last time I actually accidentally skipped this slide, but it's on the other lectures in the Boulder School. But I went straight to this slide about decoding being hard. And we showed that degeneracy is something that makes decoding even harder than classical, and it's already hard classically. So this maximum likelihood decoding is NP complete, and it's basically the same problem as classical decoding. And that in a real life quantum computer that's built out of qubits, you're not going to be able to decode perfectly. Your decoders will have to be heuristic because you simply don't have enough space and enough time to solve it, to solve this decoding problem. I mentioned that T, the thing that maps you to a particular airspace, is I want to mention that it's a destabilizer. It's exactly the destabilizer that we saw from the previous slide that talked about encoding. And so because it provides a nice way to show how you can choose those things. Right. So back to stabilizer codes. What we introduced a couple slides ago. This is also a very general concept. And it can be defined anywhere there are Pauli type operators. And if we look at our common spaces, common alphabets, this happens when those alphabets are abelian groups. So similar to CSS, in fact, namely, you have your qubits, qudits, bosonic, continuous variable systems, and rotors. All of these have Pauli type operators. They're called Heisenberg-Weil operators, I think, more generally. And stabilizer codes can be defined as joint plus one eigenspace of a commuting or abelian group of such Pauli type operators. So that's just regurgitating this previous slide. Some famous examples. For qubits, all CSS codes are stabilizers. So, our 422 code, Steen code's the smallest CSS code that corrects a single qubit error. If we enlarge to stabilizers, the 5-qubit 513 code is the smallest stabilizer code that corrects one qubit error. It's not a CSS code. And there's a bunch of famous codes here. They've been classified up to n equals less than or equal to 9 in this IBM paper. Classified up to permutations and local Cliffords. More generally, for qubits and qudits, there's effectively two types of classical code mappings that allow you to build quantum codes. One of them is this CSS mapping, which is in this context called Euclidean. We already saw this. And the other one that I'll just mention in passing is the Hermitian mapping, which arises from the ability to map Pauli operators to field elements. So for qubits, Q equals 2, and the 4 Pauli operators can be mapped into the field F4. I'm about to cover fields again, so hang tight. But this also allows you to map the underlying code into a particular classical code whose commutation between the Paulis implies a certain property for the classical code. On the bosonic side, you have the Pauli type operators are all displacements in the different various directions in the phase space. And there's actually two types of groups that you can define. Both are infinite, as in non-compact. But one is discrete and one is continuous. So if it's continuous, it's basically like a combination of different R factors. That defines a hyperplane for the code. And that's what underlies these analog or Gaussian stabilizer codes. And then if you define a discrete set of generators for a group, that defines a group Z to some power integers group, basically. And that stabilizes a lattice. That's basically you can think of it as a symmetry group of a lattice. And that gives you your GKP code. So there's really two fundamentally different types of bosonic codes um, that are both stabilizer, but one of them consists of basically Gaussian states, and the other one is exceptionally not Gaussian, namely the GKP case. And it's interesting to investigate these hybrid kind of things. And I alluded to that in a previous slide about CSS, where I mentioned that you can stick in Z homology into the bosonic setting, and doing these kind of stabilizer constructions is precisely how you do that. Well, because CSS codes are stabilizer. On the spherical front, again, stabilizer codes are only really defined for rotors, which is n equals 1. And I already mentioned the whole CSS code formulation of homological rotor codes, but there's also at least one non-CSS rotor code that's in a paper by me and some collaborators. Okay, so it's interesting to look at generalizations of stabilizer codes. They're very kind of like foundational, and they have three features about them, namely that you are a joint plus one eigenspace of a group of commuting and Pauli type operators. So namely unitary and operators. Those three conditions, we could remove one, two, or three of them, and we get some other generalizations of codes that are kind of around the corner from stabilizer codes. So here's a Venn diagram that I tried to make to organize these things with stabilizer codes in the center. And if we do the simplest thing, we just consider now the error spaces of stabilizer codes. Then we can fill out this circle. These error spaces are eigenspaces of a set of commuting Pauli operators. So commuting unitary operators, but they're not the joint plus one eigenspace because you've left that and you've went into another error space using, say, a destabilizer. So these kinds of stabilizer error words are exactly these, these examples of these codes, which are very simple. They're also called Pauli frames, and we'll get to them a little bit more. When you measure things, you're going to be hitting these Pauli frames because you're never guaranteed to be in the code space. If we now assume that we are kind of the opposite, that all we need for our code is to be in a plus one eigenspace of some set of operators. They need not be unitary and they need not be commuting. Then we get a set of generalizations of the surface code called quantum doubles and also group GKP codes, which are defined on qubits valued in non-abelian groups. So in that last line in the alphabet slide, which I haven't talked about much yet, this is where these guys lie. So the operators that define them are not unitary and they don't commute. However, they do share a joint plus one eigenspace, and that defines the code. So in that sense, they're kind of generalizing stabilizer codes. Now, let's say we have two properties. We are, did I mess this up? Let's see. Yeah, I think stabilizer error words should also be in this because, yeah, this part I think should also have, this part should also be over here because these are Unitarian commuting. Yeah, I was struggling what to put in this corner. I'm not sure what lives in this corner. So, right, so this corner, this thing that has two properties is also including stabilizer error words. These are all stabilized, or they're part of a, they're defined by a set of Unitarian commuting operators, but they're not the plus one eigenspace of these operators. And these are your union stabilizer or CWS codes. So what are those? Well, so for union stabilizer, there's a very nice way to phrase it. You basically take a stabilizer code, which is the +1 eigenspace, and then you tack on some of those error spaces to the code. So you just say, I'm going to use the +1 eigenspace and another eigenspace, and that now is my code. So you get a larger logical dimension, but now you get a little bit less error correcting power because what you had for an error space, what you had to accommodate errors, is now being used for the code. And CWS is more or less equivalent to stabilizer, but it's constructed using cluster states. Now we go to have you save two properties, but you remove the commuting one. So now you're in a +1 eigenspace of unitary operators, but that need not commute. These are your Clifford stabilizer codes. So now instead of picking Pauli's to define the code, you pick a set of Clifford operators. You pick a subgroup of the Clifford group, and and define that subgroup such that it has a +1 eigenspace that's like not one-dimensional, and that will be your code. Now, outside of that +1 eigenspace, that Clifford group will not usually commute, and but nevertheless, you can still define a code. That's why it's not commuting. So these kinds of codes, these Clifford codes include the XPXS stabilizer codes. That's just taking a particular subset of operators in the Clifford group. They also include CZ stabilizer codes, and a lot of recent work on code switching and has been basically, and magic state creation via code switching has been basically done with the help of these Clifford codes as intermediate codes. Now, the third set of two properties that we want to look at is that now you have a set of operators that commute and share a +1 eigenspace to define the code, but they're not unitary. So that's different from the quantum double case, because there they weren't commuting. This time they are commuting, but not unitary. And these are many of these extensions of the CAT codes that we've been working on. Namely quantum spherical and Tiger codes. One of their operators that you use to define the code is a set of jump operators of a Lindbladian, and the other one is some subgroup of Gaussian operations. So in some sense, they're kind of like bosonic analogs of the Clifford codes, because one of the operators, the stabilizer-like operators that is used to define them is Gaussian operations, which are analogs of the Clifford operations for oscillators. However, the other operator is a combination of lowering a polynomial and the lowering operators, and that's definitely not, unitary or even diagonalizable. And last but not least, you can use non +1 eigenspaces of sets of unitary operators, and you can actually define the code such that the operators that you would have originally thought would be stabilizers are actually logicals for the code. So in group theory, if you pick a group of operators, the +1 eigenspace is basically is exactly the multiplicity of the trivial irreducible representation on the group. Namely, the group acts trivially on the +1 eigenspace, so it's represented trivially. It's in the trivial irreducible representation. But you can pick another eigenspace for on which this group is represented, like we did with union stabilizer and Pauli frames. But in that eigenspace, you not only have the set of operators or the group of operators represented with phases, you actually have it represented as matrices, so they'll actually manipulate the code words. So you can't simultaneously diagonalize them in that eigenspace to get some ±1 eigenvalues like you can with stabilizers, because this group is not abelian. And this has led to a way of defining codes using groups of things that you want to use as gates. So say you want to use some Gaussian operators as gates or some Clifford operators as gates. So you just define the code to be their, say, two-dimensional irreducible representation that lies inside a bunch of qubits. That will define a logical qubit code, and that will automatically guarantee that every single one of those operations is represented in this two-dimensional representation on the code, so it's illogical. Well, depending on what the irreducible representation is, it can be illogical. If the representation is faithful, then every operation is illogical except the identity. And this has led to a direction that, again, defines codes using gates instead of defining codes using particular error correcting desiderata. This gives you codes that are definitely non-stabilizer, but on the other hand, that have a lot of very nice gates. And in some cases, depending on the group and on the irreducible representation, the eigenspace, the gates will there will be actually some error correcting power baked in. So there's a little bit of a dance that the group theory and the error correction do together for very certain specific groups and irreps. So I encourage you to check out, this paper. I think is one of those in that line of work. Okay, so I was hoping there would be a question because this is a lot. Feel free.
So like where do you put, Victor, let's say those kind of works where one starts with, let's say, Easton Neal, and so I think there was some work by Inkai Wuyang and Ramesh Novasag, where they start with like a bunch of classical code words, take their linear combination, and then try to find what kind of linear combinations are possible, and they would
Yeah.
or maybe about that later.
No, earlier. So those are even farther from stabilizer codes because there's not a set of operators that underlies them. They're just a partitioning of a code. So they're kind of just defined in the Schrodinger picture using states and not in the Heisenberg picture. So I would put them into this kind of partitioning framework that we looked at for CSS. So we use the same kind of theorem that they do to define the partitioning, or an extension of that theorem. And so I just wanted to allude to the simplex picture. So here, when you do this kind of CSS-based construction, you do not use any kind of operators in this particular way I'm constructing things. And when you extend this construction to just partitioning, pepperings or packings of some space, that's not utilizing stabilizer codes. Okay. Remove this. Okay.
So Victor, in that Venn diagram, basically like all these codes are the codes that are defined using like on a subspace defined by a set of operators. Like is this like kind of like the general theme of these?
Yeah. Exactly.
And do all of these have the kind of like advantage of stabilizer codes where you can easily identify your check measurements?
No, unfortunately.
Okay.
Yeah. So as you stray farther and farther into non-abelian land, you don't. So let's see. So these actually, there's been a lot of work on decoding these. So these actually do have enough, syndrome data. These generally need not have your natural syndromes that you would think they should have. It depends on the group. Well, in fact, these also have a similar issue that like their state preparation can take very many rounds because the group might have a certain structure. The group here is abelian, so these actually do have syndromes. So they're kind of like the CSS cousin, the CSS version for like bosonic cases. So this is one of the examples of Z homology I had in the previous slide. These also, they're not abelian, but they're sufficiently structured so as to have enough syndromes. Although I have to say I have not seen a lot of work actually decoding them. In particular, yeah, these general guys, story is still out. I don't think they will in general. Nobody's really looked at them in general. And here, basically you trade off all your almost all your stabilizers to be logicals. So whatever you used to define the code, right? That's set. Now you like basically forcing it, imposing it to be logical. So you're not gonna, you lose, you trade off stabilizers for logicals here. Okay, and then these are problematic to use stabilizers because now you're in two different eigenspaces. So you can't measure the stabilizers to get without collapsing the logical information. Okay.
Got it. Thanks.
So can we still like think of all of them as satisfying the subspace Neal-Laflamme condition, and maybe still like part of subspace codes?
They are all still subspace codes because they're defined using subspaces.
Like subspace Neal-Laflamme.
Now, yeah, and they all have some kind of error correction. So they do satisfy Neal-Laflamme condition. I'm not sure what you mean by subspace Neal-Laflamme. Like
Yeah,
not
so
subsystem.
yeah, so like you can have different kind of Neal-Laflamme, right? You can have subspace Neal-Laflamme, then subsystem, then like
Okay.
flocate Neal-Laflamme, and more general. So then one can generalize in the direction of Neal-Laflammes, and basically I was thinking that even Inkai kind of work will be a special case of a subspace Neal-Laflamme, because like that's what all these codes are satisfying.
Yeah, sure. These are all subspace codes. Okay, no subsystem, no flocate. The Inkai codes and the ones I mentioned on the simplex by me, Sasha Barg, and Arda Aydin, what they do is they pick a classical code so that the distance, the packing of the classical code is well separated enough to kill off the Neal-Laflamme off diagonal conditions automatically. And then all that's left is the diagonal conditions, and so the partitioning solves those diagonal conditions. The partitioning is due to these math lemmas that guarantee that these conditions will be solved effectively. Map them to a set of conditions that can be solved geometrically. It's called Terburg's lemma, Terburg's theorem. And radon theorem is a special case, which Inkai used. So those you can kind of think of them as like codes that are based on satisfying Neal-Laflamme conditions. I agree with you. And that's very different from here, where you just have subspaces defined using operators for various purposes with various definitions. Okay. Good. Yeah.
What's the upshot of losing unitarity, like the bottom part of the Venn diagram?
Right. Good. So well, it's like a necessary feature. You get to use cat state, like to have cat codes. So you need this. You need to lose unitarity because you need to basically switch your protection from discrete measurement based to dissipative, to turning on a jump operator in Lindbladian. This is not so easy, but it comes with certain advantages. Namely, the code is compact, so it's a bosonic code that's compact. If you were to do GKP, you have to worry about finite energy GKP codes and how gates act on them and how things displace them around and how you don't get back to the code space, because the code is inherently non-compact and you're trying to make it compact, like by doing finite energy versions of it. Here you get inherently compact codes. They lie on the sphere. Okay, they lie somewhere on the coherent state sphere of fixed energy. And so you could rotate them around. There's no like leakage or anything like that. There's no finite energy, anything. They're already intrinsically finite energy. But to get these, you need, you're basically stuck with this kind of dissipative process that's defined using non-unitary operators. If anybody, Andrew, anybody can think of something to put in this to make it more symmetric, I would be thankful. Offline we can think about it. That's homework. All right. Any other questions? Good. Thanks. That was useful. I keep mentioning finite fields. As physicists, we are not trained in them, so it's important to have a couple slides on them to define these qubits especially since they've been getting some traction recently. What's a finite field? Well, C, complex numbers, is an infinite field. And so it has all the properties that the finite fields have, more or less, that are used in the definition of a field. So I'm going to define this field, finite field, by defining the analogous things that C has so that you can use C to kind of wade into this finite field territory. So a finite field with Q elements is defined as F sub Q or GFQ. Q here is a prime power. It cannot be anything else. These are the only fields. GF stands for Galois field because Galois defined a lot of these things. And it literally has Q elements. And fields have basically all 4 operations defined: addition, subtraction, multiplication, and division. Okay. So this is your finite field. That's how one way you can define it. And this kind of definition touches upon how people like to think of these things as basically solutions of some polynomials. Okay. I don't like to think of it that way, but I'm not an expert by far into this. So finite fields have a trace operation defined on them. That's just the analog of taking the real part. So with complex numbers, you have a real and an imaginary part. Okay, and imaginary numbers, don't exist, so you sometimes have to come down to the real world by taking the real part. And finite fields, depending on the value of m, roughly have, m different directions in them, or like m different imaginary parts. M minus 1, and so then to kind of get the real part of all these pieces, you sum up the field elements by taking their powers of multiples of, or not of, their powers of p squared, p cubed, power, etc. That's defined as the field trace. The field also has a norm, and in the complex case, you have your 2 kind of directions, z star, and you just multiply them together. In the field case, you have your m directions, which are determined by gamma to the power of p to some power. That's m directions. You multiply them together as well. And these m directions, the analogy here is actually pretty precise. They're literally m directions that you can use to define a vector space. So in the complex numbers, you can define the complex numbers as vectors over the reals of 2 dimensions. The real and the imaginary part, you can stick it into a vector, and then you can just avoid doing I altogether. Here, if you have a p to the m field, you can do the same thing by sticking by kind of expanding it out to a vector of m elements. But now the vector over m elements will be over something simpler, which is just zp, which is a prime field, which ffp, but f and z are the same when p is prime. So just the numbers modulo p. Multiplication is defined for such things automatically, basically. So this is a very powerful technique that allows you to basically manipulate your field and shape it in whatever way you want. You can shape it as a number or a vector. And so you can inject some linear algebra if you feel more comfortable with that, as opposed to dealing with these weird, with everything baked into one number, one abstract number. So for example, given, let's take the field with 4 elements. So 2 to the 2. So P is 2, M is 2. These elements are defined as these. So I like to think of this field as just cube roots of unity and 0. Omega here you can think of as a cube root of unity. The coding theory people don't seem to like that, but you can, if you do it, it's not wrong. So omega is a cube root of unity. And here is how you can kind of unfurl this field to be a vector space of dimension 2 over the binary field. You associate the 1 element of the field with the 1, 0 basis vector and the omega element with the 0, 1 basis vector. And now you're cooking. And you can see how you can define the 4 field elements as these 4 different binary vectors. And if you then go backwards and you plug in the field elements that you associated to the basis vectors, as I do here, 1 and omega, then you will see, using cube root of unity multiplication, unless I made a typo, that I made a typo. This should be omega. This should be, well, anyway, you can do the math here and you'll get the 4 elements here. That'll be in a different order because of the typo that I put here, but you will get all 4 of them, which is the important part because that completes the association. Sorry about the typo. And you can do this with more general fields for any M and any P. Okay. So it could, but basically that's what you get. You can deal with numbers over a 4. You can deal with binary vectors over Z2 squared. 2-dimensional binary vectors over Z2. So you can use that as your alphabet for your qubit. So now your qubit cats are labeled by elements of a finite field. Finite fields are not just integers mod q. So they are different. So they lead to a different set of qubits. Field qubits versus integer mod q qubits, which are rings, because multiplication is not defined for all q, for all elements in ZQ. So you get 2 different types of qubits. They are fundamentally different, both in classical and in quantum coding theory. Okay, I can't stress this enough. Basically, all the codes that you can use, like CSS codes, are different on Z versus F. There's torsion in ZQ, but there's no torsion in FQ, because one is a ring, one is a field. Of course, they overlap when Q equals to 2. And so you get back to qubits. And they overlap more generally on prime qubits when M is 0. So Q is prime for the field case. They do not overlap for powers of primes. For example, Z4 is not the same thing as F4. Z4 is 4th roots of unity. F4 is 3rd roots of unity with 0. And that's important because the differences between these codes already manifest themselves for 4-dimensional qubits. For example, there was a paper that used anion condensation to define new phases, novel, like previously undefined phases of matter using stabilizer codes. And they did it using Z4 and the definitions thereof, and not F4. It was impossible to do it with F4. And you can incorporate a lot of phases of matter using modular qubits, but not Galois qubits. If you take Q to infinity, you can get back to your other alphabets. There's a paper about that. And you can do it in different ways. So one way is you take your ZQ. This is both done from ZQ, not FQ. I don't know how to do anything with FQ and Q going to infinity. I think it's like a fundamental no-go. So with ZQ, You can think of it as a pizza of Q slices on a circle. You could take the slices to be super, super, super close together while maintaining the circular structure of the pizza. That gives you a rotor. On the other hand, you can cut open the pizza and take the slices to infinity. You get an oscillator. And many different kind of models and codes are kind of preserved or mapped into these other continuous variable spaces during this limit. And so you can get analogs of oscillator and rotor oscillator analogs of many modular constructions. There's another equivalence between these fields that I mentioned before. It's this kind of like netting of dough that you can do to express a field p to the m as a vector of m dimensions over zp. So in the quantum world, that means that one Galois qubit is equivalent to m modular qubits. One Galois qubit for p to the m is equivalent to m modular qubits that are prime, m prime qubits. So you can do this kind of tensor product decomposition, and then you can get back to using modular qubit pallies. So effectively, what it tells you is that modular qubit pallies for prime qubits, if you block them together, they're equivalent to a Galois qubit Pauli set. So this kind of netting that I mentioned, you can upgrade it to matrices now. If your field is now, if you split the power m into m times n, so now your field is p to the mn, and you can do this thing one time, and you get a vector of n dimensions over p to the n, and then each entry in this vector is a p to the m field. You can split that itself into its own vector. That'll be a row here of over fp or zp, which in the end gives you a matrix of dimension m times n over zp. So you can kind of stretch these things out any way you want. And this is something that is done in distributed storage codes, you know, like say like AWS servers and data center codes. This is useful because I think you think of like columns of these things as like belonging to one node in the data center. And you could kind of combine them if you want, and if it's more convenient, you can unroll them. And more recently in quantum, there's been traction of using this kind of mapping to start with a query code, so a code over fields that has interesting gates, and then convert it to a prime qubit code yielding a code over ZP that has that maintains those interesting gates. So with p equals to 2, this was done in 3 different papers, and it should be in the zoo. I should have linked them maybe, but these kinds of algebraic geometry codes that are defined over f p to the m, 2 to the m, f2 to the m can be used to map it to qubit codes over Z2 while maintaining their gates and their error correction. So these are codes that have interesting Clifford hierarchy gates, diagonal ones. Okay, so that's it for fields. If there's any questions, feel free to ask now. Hope you get this is a reasonable introduction to them, so you're not completely like floored when you see papers like this. Now we go to codes that have a notion of locality, namely geometric locality. So in layperson terms, what does that mean? That means that they're check operators, those stabilizer generators I told you about for stabilizer codes, but more generally, other types of check operators. They act on a set of qubits that's constant, and meaning independent of the total number of qubits. So we're often here dealing with code families that are defined for increasing n, but their checks are defined on constant subsets of n. Now, those are called QLDPC codes. They're low density parity check codes. If in addition now we assume that all those qubits that are defined that are acted on by the check lie in a region of a small region defined in the geometry of the space, then you are geometrically local. I should also say QLDPC codes are also such that each qubit is not acted on by a number of checks that's dependent on n. So each qubit is acted on by order 1 checks, by a number of checks that are independent of n. So we're talking here about QLDPC codes that in addition have geometric locality in place. So this is your surface code and whatnot. Mathematically, these are called code. This means that you're defined on some kind of Euclidean geometry. You have a notion of like Euclidean locality, or what we have in the real world. I can also slightly relax that to do hyperbolic locality, hyperbolic geometries, and more or less things hold. That kind of geometric locality is still present there. So codes that are defined like that are ground or low energy subspaces of many-body Hamiltonians. And this leads to a whole field that, as I mentioned, got started by Kitaev of connecting topological or properties of phases of matter to properties of underlying codes. I should mention that topological phases are not the only phases of matter that are relevant to codes. There's also been some studies of codes where error correction comes from the eigenstate thermalization hypothesis, which you could kind of think about, if you know what it is, kind of think about it being related to the diagonal Nilaflam conditions. So topological orders are not the only phases that are relevant to error correction. But those will be the ones I will cover in this talk. But I encourage you to check out the zoo for some other, for say these ETH codes and whatnot. So there's a kind of a very intimate relation between the properties of the phase of matter and the underlying many-body Hamiltonian, and the underlying error correcting code that the phase defines. So if we now specialize the topological phases, these are characterized by kind of an umbrella of features. So the first question you ask is, okay, are your constituents, are your little subsystems or parties, bodies, are they bosons like qubits? Do they commute with each other? Or are they fermions? Do they anti-commute with each other? And that gives you two separate families of phases. The next thing you ask is, what spatial dimension are you working in? And these are spatial dimensions relevant to error correction. You can ask me why. The first three, of course, are relevant to us in our everyday lives. The next thing is, well, now that you've fixed dimension and the constituents, what's the way you characterize a phase is by its excitations. So you have a ground state space, and then on top of that, you like prick the ground state space, and you cause the ground states to get excited into some sort of excited states. If you're doing this locally in the Euclidean geometry, then your excitations will be small because you're only exciting some local region. And then when you play with these excitations and characterize them all, you see that they will act like they will have some dimension of their own. So for in 2D, you can have strings because you're in 2D, you can have 1D excitations. In 3D, you can have membranes along with strings. So you can have there's more freedom, more types of excitations in higher dimensions. So it's not just all about the surface code, which is defined in 2D. And what topology also sometimes manifests is some kind of edge effects that are protected. So the surface code is not one of these cases, but the quantum Hall effect, the most robust topological order, well, it's symmetry protected, but still the most useful one in the real world is actually a manifestation of this edge transport, where you have some conductivity, some electrons going around and that are very difficult to stop because of this topology. So that's kind of topology in a nutshell. I encourage you to check out these books. Very recent, very interesting area to explore. For us, the most mileage obtained from this connection between topological order and error correction is, of course, from the surface code and generalizations thereof. And there's a strong belief by some in the community, which I don't disagree with, that many of the gadgets that are the fault-tolerant gadgets that people use, or people want to use, and people define for the surface code and generalizations thereof, are actually examples or can be interpreted as things that arise from properties of the phase. And so there's a whole table here for the surface code, namely for the surface code, the code space is a ground state subspace. Stabilizer generators are the Hamiltonian terms. These are obvious. So errors, your local Pauli error cause you to excite the ground state space, and a single Pauli actually excites two terms in the Hamiltonian, and so you can think of it as exciting a small line, a line which terminates at two anyons. The X-type stabilizer constraints are imposing what's called gauge symmetry or flux conservation. So you're kind of like flowing through the crosses, and the X-type stabilizer constraints make sure that you're kind of what's coming in is conserved with respect to what's coming out. So it's the binary analog of a Maxwell gauge constraint. You can, I don't know if I should say this, but you can even maybe go as far as like a loose analogy to like Kirchhoff's law of current. But don't quote me. The Z-type stabilizer constraints are guaranteeing that you have some flux going through a loop that's a particular value, 0 or 1. And the loops can be arbitrarily large, and they all are loops, so they all have one-dimensional, boundary. They're all like one-dimensional loops. So that's called a one-form symmetry. It's a symmetry because, no matter what the loop is, it's trivial. So you can call it a symmetry. And you can define the symmetry to act on arbitrary loops, so you can change the form of it. But the loop still is a loop, so it's one form. And of course, the one here can be substituted for other things depending on, like I said before, the structure of the underlying space, the spatial dimension, etc. Logical Paulis, remember, think of the toric code on a torus. Those are special types of loops. So the Z-type stabilizers are all contractible. You can squish them down. The logical Paulis are not contractible because of the homology. Remember that. So those are often called Wilson loops in this context, in the context of gauge theory and topological order. And then last but not least, the fact that you have some protection in the surface code from local errors. You don't just have protection against local errors, you also have protection against non-local errors. But the subset of errors that are geometrically local, okay, that also has an analog in the TO world, and that actually can be stated as that the local perturbations don't distinguish between ground states. So a topological order often has this property that local perturbations can't tell which ground state you're in. Okay, the ground states are kind of defined using some kind of global correlations or global degrees of freedom. And so local perturbation can't sense that. That automatically implies some error correction on the error correction side, right, against local errors. Nil-Flam conditions are satisfied. This was formulated rigorously by what's called TO1, TO2 topological order conditions by Brave et al. And so these conditions can be now used to more rigorously define topological phases. And it's very nice because literally one of those conditions is basically a Nil-Flam condition. So, okay. There's more to this analogy. Sorry, let me, I should maybe do, which slide should I, yeah, let me just keep going. There's more to this analogy. Not only are errors and the code properties, code parameters defined using analogs in the phases of matter world, like I said, gadgets can be defined, can often be associated with underlying properties of the phase of matter. So here's a general slide comparing different gadgets that people use. So many kind of transversal gates or constant depth gates on this side of a code, and even qubit permutations, certain qubit permutation gates are actually examples of manipulations of something relating to the phase, say the anyons, the holes, the defects, can be interpreted as braiding or manipulating these things in some way. And together, all the different ways you can manipulate things like this is called the mapping class group of the underlying geometry that the code is defined on. And there's a belief that basically any constant depth or fault tolerant gate can be thought of as unitary gate can be thought of as being associated with some element of the mapping class group. Weight reduction. So this is this is a gadget that takes a stabilizer code with checks that are non-QLDPC, that are act on many different qubits whose number is dependent on n, and you chop them up into checks that are smaller. So you get a new code with smaller checks, namely you've reduced the weight of the stabilizers. This can be thought of as gauging. So as you see, the word gauging here is defined a lot. So in this context, gauging means chopping up a large operator into a small one. Okay, so let me introduce gauging. If you go back to field theory, gauging is what is used to define a gauge theory from a theory that just has a global symmetry. So if you have a global symmetry, it has to act on everybody. So it's not this like one form, loop symmetry. It's a global symmetry. It always acts on the same qubits at every time. But if you have some model with these black dots as the subsystems, you can then promote that symmetry to a local symmetry, or quote unquote gauge it, by introducing new degrees of freedom called gauge fields at the links between your original matter fields, and defining a coupling between the gauge and the matter such that what used to be the global symmetry can now act locally. And in field theory, this is how they do it. And so this term has kind of been borrowed from there and taken very, very far, almost to the point where you shouldn't be using it. But essentially, the idea of promoting a global to a local symmetry by kind of chopping it up is now done to these other types of things in quantum error correction, namely large weight stabilizers and large weight logicals, and gadgets that fault tolerantly measure these large weight operators using smaller weight operators can be thought of as arising from a gauging procedure that is applied to the large weight operators in the underlying code. Okay, I hope that makes sense. Please ask questions. So in that context, what used to be those gauge degrees of freedom in the context of field theory now become extra ancilla qubits that you introduce during your gadget procedure that you use to measure some large weight operator. So ancilla qubits are often associated are now playing the role of this gauge degree of freedom. Lattice surgery, which you may be familiar with, is effectively measuring a large weight, logical of 2 copies using some ancilla scaffolding or gauge qubits. This is shown in the red here. It's explained in this paper. It can be thought of, so lattice surgery as a gauging a particular operator, which you can also think of as a symmetry, the logical. Magic state preparation, so the idea of magic state cultivation and code switching to get magic states can be thought of as gauging and then ungauging a symmetry. So you first introduce a scaffolding of ancillas to gauge the symmetry. So you measure it, and then you have an enlarged code. You've switched into a larger code. And then you get rid of the ancillas, the gauge degree of freedom, by measuring them, and you've switched back into the smaller code. And by this breathing procedure, switching back and forth, you get a magic state. And you could do this fault tolerantly if everything is kind of geometrically local. Okay, so that's kind of gauging in a nutshell. It's still being worked on. There's still some, you know, work to do, kind of unifying all these things, but there's been a lot of work on this, and gauging has gotten a lot of mileage in the fault tolerant community. So if any questions, definitely please ask.
When you describe gauging as breaking a high weight object into small local pieces, is there, like, are you basically using some sort of boundary conditions to put the pieces together, like some sort of matching conditions where they overlap?
Yes, good.
Okay.
Good. The pieces have to be such that when their little checks are multiplied together, you get back the large weight operator. Right? Because if you don't, then you're not measuring that large weight operator. You need to make sure that when you measure the local pieces, you get some eigenvalue such that when you multiply them together, you can infer the large weight operator. And that's one of the conditions, right? That you actually are splitting up the large weight operator, not something else. Good. Okay. So I mentioned that there are generalizations of the surface code, and I'm going to mention some of them in this slide, which is new. So definitely ask questions. So the surface code is an example of a Z2 topological order, meaning that, let's see, how much do I want to say? Well, the anyons, so the E and M excitations, are described by an object that is defined using Z2. It's called the quantum double of Z2. It's a certain algebra that combines your X-type and your Z-type pallies of a qubit in some kind of weird way. I don't want to get into it. But basically, given this group Z2, you can define the anion structure of the underlying surface code. And the anion structure is not Z2 because both E and M are each Z2, so it's Z2 times Z2. But more generally, that Z2 times Z2 structure is called the quantum double of Z2. And you can do this with any abelian group, Z3, Z4, Z17, Z2 times Z4, Z3 times Z2, etc. And you get G topological order, abelian G topological order, or an abelian quantum double. Okay. All of these are just combinations of qubit surface codes. So they are stabilizer codes. They can be realized as stabilizer codes. So I'm just going to call it right off the bat an abelian quantum double stabilizer code. Okay. Well, so one way to extend this is to just consider non-abelian groups, right? So now you have just a normal quantum double code. You can call its underlying topological order as G topological order. The anyons are characterized by the quantum double of G. Now what happens when you do this is you lose unitarity. So this is one of the examples I showed in my Venn diagram. This has stabilizer type operators, which stabilize the code as its joint plus one, as their joint plus one eigenspace. However, the Z-type stabilizers are non-unitary. They are now actually MPOs, whose bond dimension depends on the group. And the X-type stabilizers are non-commuting, but unitary. This quantum double code is defined on qubits valued in a group. So this is an example of a group alphabet, use of a group alphabet, an important use case. And this, I've only mentioned all the bad news. You lose unitarity, you lose commutativity. What's going on? Like, why do we even care? Well, you gain the ability to do some interesting gates. So there was a very recent paper that figured out how to do non-Clifford hierarchy gates for quantum doubles based on dihedral groups, which are the minimal non-abelian groups that you can have, basically. They're nearly abelian, so like the smallest step you can take from abelian. And even already those groups, you already get interesting gates. So it's kind of the trade-off that I mentioned in the non-unit, the stabilizer Venn diagram, where you can assign some of your stabilizers to be gates. It's maybe not quite that technically, but similar in spirit, that you could still have stabilizers here, but you break a lot of their nice properties like unitarity and commutativity, but you gain, that's a price you pay, but then you buy the ability to do interesting gates fault tolerantly. So there's definitely more to investigate here. I mean, given how recent this work is and how long these have been around. So both of these were started by Kitaev in his seminal paper like over 20 years ago. And so there's a further extension of these where you now define the topological order not just using a group, but using what's called a twist or a cocycle, 3 cocycle. So now I'm not the expert at this, but when you define a code on a cellulation of a manifold, which is what we're doing here with Euclidean codes, right? We want some kind of Euclidean locality. There is a consistency condition you want to ensure such that the model is independent of the cellulation you pick. So you say I pick simplices, I pick squares, I pick whatnot. I pick cubes, simplices, I pick different things. There's a condition on the center of on each of these cells that I need to ensure such that the code is independent of the cellulation. And this implies defining this cocycle. This basically forces you to use these 3 cocycles for 3D codes, 2 cocycles for 2D, etc. Sorry, 3 cocycles for 2D. To define the code in a consistent way. That's not necessarily a rigorous explanation, but it's just something to give you the flavor of this, that there's this extra piece to kind of ensure that you really have like a topological order defined more general than just using the bare group G. So this will be a trivial cocycle here. You can extend this to non-trivial things as well. And this is called a twisted quantum double, or a TQD code in 2 dimensions. This is called a twisted quantum double. And the reason I wanted to go through this painful process is because if you now maintain the twist, but now restrict the group to be abelian, you actually get another set of very actively studied codes that are also very useful. And you make contact with extensions of the stabilizer formalism. So you can go to this abelian TQD section by just taking an abelian QD and adding a twist. So now you're dealing with ordinary qubits and qubits. Say, for example, if the group is Z2 cubed, remember here we just have an abelian group. So now we just pick 3 qubits at each site. But now we add this twist, we get not a Pauli stabilizer code, but a Clifford stabilizer code. Okay, and this is an example of this XS stabilizer code that I mentioned before. I do want to mention that everything's in the zoo, if in case I haven't linked the paper. So this makes contact with Clifford stabilizer codes, and these codes are also interesting. I mentioned before, they give you this kind of ways to distill magic states. Those papers by Margarita Davidova et al. Go through these kind of twisted abelian TQD codes to get to their gadgets. Also, self-correcting memories in 6 dimensions were realized using these kinds of twisted abelian TQD codes. I want to mention that even though the word abelian is here, I want to mention about the structure of their excitations. So if we go back to the abelian case, all of these kinds of abelian QDs, abelian quantum doubles, give you abelian anyons, which means the anyons actually don't commute, but they don't commute up to a 1-dimensional phase. In the quantum double codes, now you have what are called non-abelian anyons. And now those are defined such that when you actually try to combine them together, you get a fountain of different anyons. You get more than one anyon possible. For the abelian case, when you combine 2 things together, their phases just multiply. You don't get any kind of multiple anyons. You just get an anion that's defined as the combination of the two, E times N. But in quantum doubles, when you combine anyons, you get multiple cases. And that's called a non-abelian anion topological order. And here, what's interesting is that when you twist abelian groups, in some cases, you actually get non-abelian topological orders. So these actually give you sometimes the similar or the same topological orders as this side. And this is one of the ways you can, this is actually behind these magic state cultivation like code switching papers where, or extensions of cultivation to non-abelian cases like this Davidova paper, they actually use this kind of abelian TQD order that is equivalent to a dihedral topological order. So again, dihedral is present here, but now for a different gadget. So anyway, this, I just want to flash that this is very interesting and active work. These are these maintain unitarity of the stabilizers, but lose commutativity. These lose commutativity and unitarity. So they're very different types of codes, but together they're kind of unified by this twisted quantum double picture. They're all different sides of this twist TQD elephant. This TQD elephant can in turn be generalized to arbitrary dimensions in what's called a digraph-Witten gauge theory. So this thing is just the same thing as this, but defined for arbitrary dimensions using groups and cocycles. So digraph-Witten to 2, restricted to 2D gives you twisted quantum doubles. So everything here is defined using group qubits. So this is a group qubit code. Alternatively, you can go to what people really use to characterize phases of matter.
So can we do, Victor, like, so let's say, you know, like, I mean, okay, so I have to read these papers and all, but let's say I want to, you know, like, tune this hierarchy, and let's say I go to the smallest level, and I'm not interested in, let's say, stabilizer code, but I'm interested in flocate code. Can I again build this kind of hierarchy, or has anybody already done that? I mean,
good question. I'm not going to claim I know the literature 100%, but I haven't seen any abelian TQD flocate codes. I believe people have tried, are thinking about non-abelian quantum double. So this side, maybe you can fill in with something, although no paper comes to mind. This side, I don't know of anything, and certainly this side, I don't know. But it's a good question to extend flocate codes to. I mean, but flocate codes are stabilizer, right, Kishore?
I mean, but it's like dynamic, right? The subspace keeps changing, so it's like I mean, it need not be like periodically changing, like some aperiodic dynamical code, for example. I can start with, or I mean, like I don't need to even go there. Let's say I start with, you know, some subsystem code. So I have some subsystem structure, and there is a subspace where which are, you know, like so let's say even for subsystem codes, you know, like, I mean, have people looked at this kind of twisted quantum double things and abelian?
Right.
Mm.
Yeah. So there's a problem here because of literally the definition of the anyons that when you try to measure things, you can get multiple outcomes where you used to have just one outcome here. So basically, it's going to be hard to get guaranteed periodicity in a flocate type code because now every time you measure, you have multiple paths you can take. So this is part of the reason these non-abelian quantum doubles are hard to initialize, and it's probably, and I think it's part of the reason it's hard to make flocate codes out of them. So that's what's tricky on this side, because this side, the abelian TQD side, also realizes the same topological order in some cases as the QD side. Those would be difficult. Those are called type 3 cocycles. But with type 1, type 2 cocycles, maybe you could define some flocate codes. That's an interesting idea. But those are not realizing non-abelian topological orders, so it's not clear what they would buy you. But they might get you new flocate codes, maybe. Yeah. Yeah, good question. But the other thing you have to worry about is that you're going to be extending flow K codes to non-stabilizer codes in both directions anyway. So that's an extra degree of complication. All right, so that was all the good news. The bad news is that when you restrict your checks to be geometrically local, you can't get the best possible codes. So you can't get those asymptotically good codes that I mentioned before. So there's something called the Bravi-Poulin-Terhal bound on codes on d-Euclidean dimensions, so d-dimensional square lattice, or more generally, some kind of lattice in d dimensions. And this bound means that it implies that basically the best code you can get is one with over n qubits whose logical number of logical qubits scales as n to the d minus 2 over d, and whose distance scales as n to the d minus 1 over d. The surface code saturates this, and this is again for stabilizer codes. And so you're limited by the Euclidean dimension. I'll get into subsystem codes in a bit, but the subsystem codes also have a bound, Bravi-Terhal bound. That's the following. This paper plotted everything very nicely. There's an analogous bound on classical codes, actually. And it basically kind of organizes the bounds in this way using the log of base n of k and log base n of d. And so here's your playground. This is how much you're restricted by. And there's been some work saturating these bounds via various different constructions. But this is as best you can get. Doesn't mean it's a no-go. You know, there's still thresholds and whatnot for these codes, but if you're just focused on code parameters like rate and distance, you're not going to be able to get asymptotically good codes when you restrict your checks to be geometrically local. Moreover, the gates that you do, I mentioned like there's lots and lots of different gates you can do when you borrow from the topological order that underlies the code. However, those gates are also limited. These are called, so the bounds that limit the gates are the Bravi-Koenig and the Postowski-Ishida-Bravi-Koenig bounds. They basically tell you that any kind of fault-tolerant gates, these mapping class group gates that I mentioned, for codes of Euclidean dimension d, with some kind of distance, you know, some kind of increasing distance increasing with n, have to lie in the dth level of the Clifford hierarchy. So they have to kind of be only d times more complex than your kind of Clifford group. The Clifford hierarchy here I defined for level k. It's just those unitaries that conjugate pallies such that the resulting conjugated pally is in the level below. So the first level is the pally group itself. The second level is the Clifford group because it can conjugate pallies up to Cliffords. The third level is is not a group anymore, but it conjugates pallies up to the Clifford group conjugates pallies into pallies. The third level conjugates pallies into Cliffords. And you know, these are effectively kind of finer and finer grained gates that you can use to trotterize your general logical operation that you want to use in your algorithm. So the higher the hierarchy, the finer the gate is, the more precise it is, and you know, presumably the shorter the compilation time, so the better it is. Third level is enough to give you universal computation already, so people maybe focus on that a lot more. But you know, you need a code in 3 dimensions to do that in a constant depth circuit. Unitary. If you upgrade to hyperbolic geometries, there's a paper by Delphos, which gives you a small improvement, log k improvement. For example, here in 2D hyperbolic geometries, this is what you can get. And maybe Kishore on your note, like there have been people who studied flow k codes in hyperbolic geometries as well. Maybe you were even a co-author, I don't remember. Yeah, so if you relax the hyperbolic geometries, you get a small improvement, but you are now in a hyperbolic geometry. Good luck building that in the lab. Right. So that's the bad news. So that ends my subsection on geometrically local codes. Now I'm going to move on to subsystem codes and the like. So if you have any questions on the topological stuff, please do ask now.
So Victor, can I think about this group of topological order as the syndromes on the yeah, the syndromes basically like the Z2 is just 0 and 1, and then if you go to qubits, then you get 0, 1, 2. Is that like a way to think about it?
Yeah, the anion types that are elements of this quantum double are basically your syndromes. So for a billion quantum doubles, they're basically going to be some kind of Curie, mod Q variables associated with these anions. They're going to be like, everything's going to be a root of unity because everything is abelian. So it's abelian and has finite order. So yes, it's going to be some modular syndrome arithmetic. When you go to these quantum doubles, unfortunately, the non-abelian quantum double is kind of a messy object. The anions are now defined via its irreducible representations, which are in turn defined using data of the group. So there's like, and the irreps are now for non-abelian groups not labeled by some kind of root of unity labels. So the labels become different, and there's not a nice structure on the labels that you have.
But is it still kind of like this syndrome kind of thing, like the thing that you see when you kind of like measure for errors and stuff?
Yes, so you still your syndromes are basically these anion types.
Okay.
That's what yeah. But the point is, my point was that the anion types are now no longer as simple as before.
Right.
But there are ways to there is syndrome data for quantum doubles, okay? So and there is syndrome data for some of these for these XS stabilizer codes as well. I'm not sure for general abelian TQDs have been. Yeah, I think that, yeah. So if type 1, type 2 are just abelian, that's fine. If type 3 are just related to this, I think it's also fine. Yeah.
Thanks.
Actually, now you think about it, I don't know if anybody's looked at syndromes for non-abelian G and a twist. Okay. That I don't know. And then, okay, so I didn't mention this. I should mention this. The string nets, these are now category based, and they give you ways to define exotic qubit codes like Fibonacci string nets and semyon models double semyon models that now basically, as far as I can tell, lose stabilizerness completely. They're still commuting projector, and there's been some work studying these things, but you pay a higher price now of losing the structure of stabilizer codes. You're as far away as possible, but you gain now universal topological computation using braiding and fusion of these anions, even for something like Fibonacci anions. So this is the part that's least studied because there's very little structure there. It would be nice if anybody's interested to work on identifying as much of a stabilizer-based structure as you can out of these. And I have some notes on that. I'll be happy to chat offline. All right. If there's any other questions, just interrupt. Now, the next part deals with another set of structures, namely, what are all the different types of logical structures that a code can have? So we've mentioned subsystem codes already. Those of you who don't know, this is the slide for you. So, so all the different types of encodings. So I'm going to have all the different types of encodings here listed as columns, and the second row is going to kind of give you a structure that you stick into this corner of your density matrix, which I'm organizing such that it's the actual code. So a subspace code, what I've been calling a quantum code, is defined to be just everything shaded in here. So let's say for a qubit, I shade in the 4 elements of this density matrix. And here I'm putting a Q at the 4 elements of this density matrix, okay? So this is a logical qubit encoding. All of this space is taken up, okay? It's a subspace encoding, so there's a logical qubit, so there's a 1 logical degree of freedom here, 1 quantum degree of freedom, namely a qubit, because all superpositions are allowed. There's no kind of classical degrees of freedom, and you'll see how these pop up later. And there's no subsystem degrees of freedom because there's no tensor products or anything. It's just this quantum space. Now the next thing is if we kill off the off diagonals of this qubit, and we get a classical, then we get a classical. So now we don't allow superpositions between, the 0 and the 1 of this qubit, but we do allow mixtures. And the mixtures are parameterized by a number between 0 and 1, a probability of getting C1. And that's equivalent to a classical bit. So you can fit in a classical bit here. So there's no quantum degree of freedom. There's a classical degree of freedom, a bit. And again, there's no tensor product structure. You just have a direct sum. Okay. Now we can double this classical guy and inject a qubit worth of information in each of the C1 and C2 components. So now what that gives is a hybrid code. So this is not a 2-qubit code. Why? Because I've killed off the off diagonals. I don't allow you to use them. So I can't have arbitrary superpositions of 2-qubit states. Instead, I have a single qubit in this direct sum factor and a single qubit in this one. And so I have all the qubit degrees of freedom in each of the factors, but now I can also so that gives me that gives me 1 qubit worth of information. And then I can reweigh the factors to get a classical bit. Okay, because I can have mixtures between the two. That gives me a classical degree of freedom. So this is an example of a hybrid code. It has quantum and classical degrees of freedom. All right. Next one is, now finally I get to a tensor product description. So now I blow up this hybrid code to include all of these 4 coherences as well. So I get a bona fide 2-qubit quantum code. Now I split this 2-qubit quantum code now as a tensor product of a qubit and a qubit. And furthermore, I now use the second qubit as some kind of like, not ancilla, but what's called a gauge qubit. I hate using the word gauge because we already use it for something else, but unfortunately here is it comes out again. So this qubit I'm not going to use for logical storage, for storage of information. I'm going to use the first one, but not the second one. The second one I can manipulate as I see fit. That's why it's called a gauge, because it's free to manipulate without affecting the logical information. And this is called a subsystem code. Okay. See, there's a tensor product now popping up in this 4-dimensional space. Okay. And now I can do that for each of my factors in the classical code. And this more generally is called an operator algebra code. It's a direct sum of direct products. Okay, it's got everything you want. It's got a classical bit, it's got a subsystem, it's got a gauge qubit, it's got a quantum bit, what have you. And there's been some, work developing very general theories for how to decode a code in these kinds of codes. Okay, so do you think this is all that can be sent? Have we exhausted all the possible structures? Yes or no? Anybody?
I would vote
So the
for
answer,
no.
you will vote for no. What do you think we've left out?
No, I mean, still, okay, my favorite thing, dynamical codes, right? The subspace is still fixed. Or one would want to change that, the way we did in strategy code, for example.
That's fair, yeah, but the instantaneous subspaces are all going to be of this type.
Sure, yeah.
So we've missed, yeah. What were you going to say?
I was thinking if there were like tensor product structures, but with restrictions like symmetry, like exchange symmetry, or that kind of thing.
Oh, well, that's a good point. Nobody studied that on the logical level. Like, if you basically have 2 qubits or like, 10 qubits, but you impose some kind of symmetry sector such that the resulting space is not a tensor product, it's a subspace of it. I mean, in some sense, that's going back to this, where you just have a subspace defined. Yeah. But yeah, that's basically kind of like a stabilizer like condition such that the +1 eigenspace is some space, but now you can't decompose it any which way. It's just a space like a blob. But a good question. Right, we forgot entanglement. So there's a whole cottage industry of people doing studying codes, studying how much power you gain when you now transfer information over a channel where you have some pre-shared entanglement between sender and receiver on the side. And this is relevant because, stabilizing entanglement is one of the tenets of quantum science. And so there are protocols to do that reliably. And this is what people are trying to do with a lot of this quantum networking business. So it's not difficult to imagine that you can have such a situation where you have a channel and then on the side you have another channel where you've stabilized some entanglement. And now what do you do with this channel is the question that these people try to answer. And you can try to answer this question for all of these structures. Okay, and there was some work last year's QIP studying this, which is why I have this slide. A pre-shared entanglement basically gives you more power. I mean, it should, right? And the question is how much. So these kinds of error correcting codes are called entanglement assisted. Right. So now let's go to the simplest case, which is this subsystem code.
So basically,
Yeah.
this entanglement, is it like some quantum memory or something?
The entanglement?
Yeah, this pre-shared entanglement, like
It's just a bell
Okay,
pair
it's-
or some number of bell pairs that's shared between sender and receiver before the sender sends anything.
so basically in the quantum computing setup, it's more like I have some noiseless register where there is some, like entangled state I preserve or something, like some dynamic entanglement or something. Like I can think of in the Alice Bob setup, but let's say I'm trying to build a quantum computer and I'm trying to think of this entanglement assisted codes.
As what? And this think
So
of this
so
entanglement
basically,
as what?
yeah. So like what does that mean? Like let's say if I'm trying to think not in the setup of communication, but in the setup where Alice, like yeah,
Storage.
does the either storage and then later like decodes. Yeah.
Well, then your entanglement will be, that's like Tenet, the movie Tenet. You have like a entanglement in time. Like
Yeah, like some dynamic
yeah, I don't
entanglement, something that people ever look at. Yeah.
Or
I don't know
is
if
it
it makes
like
sense anymore.
is it like
I
you
mean,
have
that's what.
some as Kishore said, I guess you can think of entanglement as being like good quantum degrees of freedom that you can rely on, right? Storage. So is it that instead of just encoding and decoding, you also have like some additional quantum degrees of freedom that are allowed to participate?
Basically this extra register that
Yeah.
that you kind of trust. Yeah.
Well, yeah, I don't know. I'm a bit confused about how you do this in time, because then your pre-shared entanglement is like with future. So
Yeah, so it's like dynamic entanglement, like entanglement in the temporal degree of freedom.
yeah, I don't, that's like kind of like a quantum correlation. Like usually noise can have such correlations, but like I'm not sure. how you
I
would
mean,
be
in
allowed
that
to
sense
have.
also, I would say that this maybe advertising this strategic code, like will kind of capture that also. Let's say if you have this
Sure,
entanglement in the
sure.
documents.
Sure, yeah, you do. But physically, it's hard for me to interpret it. But yeah, interesting to think about.
So if
Um,
you have the same noise on your entangled pair, then would that mess up the the entire thing? Because now you need to encode your entangled pair in some code to suppress that noise.
yeah. Good. Yeah, so it's it's kind of like metrology with with a clean qubit, right? It's an issue, right? Like the entanglement is kind of assumed to have already come from some kind of strategy that's fault tolerant so that it is perfect. So I'll just start on subsystem codes next time.